This is an example of an entropy problem. Find the change in S, the entropy, for 1 mole of oxygen gas as the temperature is increased from 56 Kelvin to 298.15 Kelvin at a pressure of 1 atmosphere. And it tells us that the heat capacity of oxygen at 1 atmosphere is modeled in 2 different temperature ranges, and that it boils at 990.20 Kelvin in 1 atmosphere, and what the enthalpy of vaporization is. This requires us to break down this information and do it 1 part at a time. So I'm going to first start with the lowest energy transformation. So from 54.39 Kelvin to 90.2 Kelvin, where it boils, it's modeled in the following way: that the heat capacity is 81.268 minus 1.1467 times temperature plus 0.01516 temperature squared minus 6.407 times 10 to the minus 5 temperature cubed. The units on this expression are joules per mole Kelvin. So in order to have this make sense, I'm going to point out that this 81.68 is the equivalent of our G coefficient. This negative 1.146 is our F coefficient. The 0.01516 is our E coefficient. And this last 6.407 is our D coefficient. So we've done this already in the model. And so the change in entropy is the integral of going from T1 to T2, and I'll be really explicit here. The first temperature is 54.39 Kelvin, and T2 is 90.20 Kelvin. And now I have to integrate this function of the molar heat capacity as a function of temperature divided by temperature times dt. And so when I substitute in this expression, I have to figure out how to do this. I'm going to point out that this becomes integrating from T1 to T2, G divided by T dt. And I know what these numbers are, so I'm going to use the shorthand for a minute, plus F dt. So I'm dividing the T by dt, and the T will go away, plus E, I divide the T squared by T, and I get T times dt, plus dt squared, because it had been cubed, dt. And all of this I have to integrate, and the way to integrate this is to integrate each individual term and then sum them up together in the end. So in order to integrate, there are 2 things I need to know. One is from T1 to T2, the integral of any coefficient divided by T times dt is equal to that coefficient times the natural logarithm of T integrated from evaluated from T1 to T2, which is A times the natural logarithm of T2 minus the natural logarithm of T1. And this is also the natural logarithm of T2 divided by T1. That's an identity property of logarithms. And then the last one, and I'll put it over here, is that the integral from T1 to T2 of a t raised to any power dt is equal to 1 over n plus 1 times a t to the n plus 1, the second temperature minus the first temperature, and that lets us evaluate this, or T to the n plus 1, T2 minus T1 raised to the n plus 1 power. Now that we know this, we can actually integrate each of these pieces and add them together. So now that we've made some space, we can continue to solve our problem. The change in the entropy upon integration, this is our coefficient g times the natural logarithm of t plus f times the temperature plus 1/2 e times the temperature squared plus 1/3 our d coefficient times the temperature cubed, all evaluated between T1 and T2, which means you calculate the value at T2, subtract off the value at T1, and when we do this, it turns out to be g times the logarithm at T2 minus the natural logarithm of T1. I'm going to add f times the change in the temperature. I'm going to add 1/2 times the e coefficient times T2 squared minus T1 squared, and I'm going to add in 1/3 times the d coefficient, T2 cubed minus T1 cubed. I'm going to solve this problem in Excel, so look for the entropyExample.xlsx, but this particular form I can use in both of the temperature ranges where it is changing, 54.39 up to the boiling temperature of 90.20 Kelvin. And I can use this with different coefficients in the range of 90.20 Kelvin to 298.15 Kelvin. And so now I only need to worry about the entropy change when I boil the liquid. And for that, I know that the enthalpy of vaporization is equal to the enthalpy of vaporization. That's an H. And that's under standard pressure conditions divided by the boiling temperature. And since we were given the enthalpy of vaporization, that's 68.15 kilojoules per mole. And I'm going to divide it by the boiling temperature of 90.20 Kelvin, and I find that this turns out to be, 6.815 kilojoules per mole. This is 75.55 joules. I converted between kilojoules and joules. There are 1,000 joules in a kilojoule per mole Kelvin. And then I'm going to add this enthalpy of vaporization to the two entropies for the temperature change, and that'll give me the overall entropy for the change going from 54.39 Kelvin to 298.15. Again, look for the solution to this in the entropy example Excel file.